Okay, so we're currently recording. Okay. So chapter 6, does anybody have any questions with chapter 5 before we dig into chapter 6? Are we all good? Okay, so let's go ahead and take a look at chapter 6. So one of the things that I want to do for we'll take a look and see what it looks like, how quickly we move through these energetics chapters. I wanted to move pretty quickly through these chapters because what I want to do is I want to bundle these energetics chapters as a take home. And I wanted to do a little bit of work on them here since schedule wise we're doing okay. And so I wanted to sort of move through these really quickly so that we could have a chance to sort of take a look at these. And then what I wanted to do is I wanted to do exam 3 on ultimately what exam 3 is going to be is going to be on the next set of chapters 10, 11, 12. So that's kind of what I'm shooting for. So I want to give you a little bit of support for the energetic stuff, which I'm going to bundle as a take-home exam. So I'll give that out to you guys probably one of these on one of these Fridays when we meet. So that's kind of what I'm shooting for. So let's go ahead and get started. First of all, can you guys see the slide okay? Good. That means you can hear me as well. Okay, so let's go ahead and take a look at chapter 6. So chapter 6 is basically getting into energetics, right? So basically what we have is now the first of this installment, the series of chapters where we're going to be talking about energetics a little bit. And so that's kind of what we're talking about here. So I always love this chapter, right? Because it always starts off with driving the point home, right? You got this cute little giraffe who's pretty well mutilated and dismembered, and you got this little lion here basically just gnawing away on what used to be one of the giraffe's bones. So, right, why are we doing all this? Well, the reason why we're doing all this is for energy. And so basically when we take a look at chapter 6, what we have is essentially a chapter with a series of ideas and concepts in it that sort of helps underpin the concept of energy, and then sort of ties it all together into sort of our larger energetic plan, which is then basically chapter 7 and 8. And so in this particular chapter, last chapter when we talked about the energetics of passive transport and active transport and things like that, we talked a little bit about how energy underpins that, how we have the second law of thermodynamics involved in there, where you're basically installing order, requiring energy in order to impose that order. And so that requires us then to have an energy plan, and this is kind of the beginning of that. So the idea then of the flow of energy, and this kind of leads off of that discussion that we originally started last chapter, was what exactly is energy, why do we need it, and why is it so important? Well, it's important because ultimately when we take a look at energy itself, it's defined as the capacity to do work. That's actually a physics definition of energy. anytime you want to do anything kind of important or cellularly significant, you have to have energy to do it. Now, when we take a look at energy itself, we have two main forms of energy, right? We talked a little bit about this already. We have potential energy, which is kind of that energy, that stored type of energy or energy position. And then, of course, we have kinetic energy, which is the energy that's released as that potential energy is released, right? So we have that kind of kinetic energy. And there's different types of forms of energy that we have. Some kinetic and some not, right? So we have mechanical energy, heat is a type of kinetic energy, sound, electric current is kinetic, light is kinetic, radioactivity is kinetic. So there's different types of kinetic energy. So when we're taking a look at light, it's actually a form of kinetic energy. And so when we see energy, we want to quantify it. We don't get too deep in the woods on this one because it starts to get into the physics of energy and things like that. But we do want to understand a couple of things. For instance, right, when we take a look at energy, we need to be able to measure it and sort of wrap our mind around a little bit. And so we do that using a measure of heat in this case, which is the calorie. And so when you take a look at the calorie, that's basically your measure of heat. And so 1 calorie is basically defined as the amount of heat that's required to raise 1 gram of water 1 degree C. Sounds very familiar, doesn't it? Sounds a lot like specific heat. So it's basically a unit or measure of energy itself. Now, in the energy discussion, we have two different types of calorie that we actually look at. First of all, there's calorie little c, which is essentially a discrete measure of energy. This is kind of what you would measure, like, for instance, if you want to know how much energy is in a chemical bond, right? There'd be little calories. A big calorie is basically a nutritional measure of energy. And so this is a little bit different. As a matter of fact, a big C calorie is essentially equal to 1,000 little calories. So actually, one big C calorie is equal to 1,000 little C calories, or 1 kilocalorie. So actually, when you take a look at the calories in your nutritional stats of food that you look at, it's big C calories. So we talked a little bit already about thermodynamics. Thermodynamics is essentially the branch of physics that deals with energy, and so how energy is changing and transforming, and the laws of energy that govern energy, right? So we have three laws of thermodynamics. So the first one is the law of conservation of energy, right? Either energy in the universe is neither created nor destroyed; it only changes form. And of course, we talked about the second law of thermodynamics, which is the law of entropy, right? That is basically that everything proceeds to its lowest energy state. And so that's part of what drives this idea of potential energy, which we always see this as sort of an example of potential energy and kinetic energy, in the sense that somebody's going from an area of high energy down to an area of low energy. Whereas before at the top, they're full of high potential energy. And then as they go down the slide, they're releasing kinetic energy, but they're also going to a state of lower energy. So it's kind of a spontaneous type of a thing because of that drive toward a low energy state for all systems to be able to maintain that. And so when you take a look at energy, then that's kind of the basic physics of energy that sort of underpins and writes the rules for all of energy that we utilize in biology. And then we can basically take a look at energy flow as it's moving throughout biological systems or between organisms, from the ultimate source of energy, which is the sun, to ultimately how energy is basically dispersed throughout all of the organisms, including the primary producers, which are plants, whose job it is to sequester the energy in the form of the sun into a useful organic molecule, right? So that's basically the job of plants, and that's what photosynthesis is about. We're going to talk more about that in chapter 8, so I don't want to basically belabor that point here. So essentially, you're going to be taking the sunlight, which is a form of kinetic energy, and you're going to be bundling it up into chemical bonds, which is a form of potential energy. And it's that potential energy and chemical bonds then that we want to actually get a hold of and be able to use for our biological processes. So just to kind of refresh, remember we did talk about redox reactions in chapter 2. However, we want to touch base on these because these are important, right? So if you recall, in a redox reaction, this is a situation where you have essentially the transfer of energy, or in this case, specifically the transfer of electrons from one from one atom to another. And so when you're transferring this energy in a way where you experience a loss, then that's oxidation. And if you transfer this energy in the form of electron in the way that you gain electron, then that's basically realized as reduction. And if you gain electron, then since you have that energy, it basically puts you in a higher energy level than from the oxidized. So the oxidized actually represents the lower energy level, and the reduced form represents the higher energy level. And so you kind of always have this sort of back and forth. So that when you take a look at oxidation or reduction reactions, you're essentially just passing these electrons on from one atom to another, and they're typically paired. You have a giver and you have a taker, right? That's typically always the case in a redox reaction. And sometimes you'll actually have a series of this, right? So for instance, here's an example where you have two molecules, A and B. And in this case, what's going to happen is A is going to be essentially the donor is going to give up an electron. So it's going to give an electron to B. So B is going to experience an electron. So it's going to be added this electron. So since it's got an electron, then B has been reduced. And then since A has lost an electron, A is oxidized. So you can see in both cases, you have basically a chemical reaction where one molecule experiences a gain of electrons, the other one experiences a loss, and that's essentially redox reactions. So just to kind of, for purposes of technical coverage, the first law of thermodynamics is essentially the law of conservation of energy. That is to say that energy is not created or destroyed. It only basically changes form. That's pretty much all it is. So the total amount of energy in the universe is essentially a constant, so it doesn't change. However, when we convert things from one to another, it's lost as heat, and heat essentially is kind of the great balancer, and it is a form of kind of kinetic energy. So sometimes when we're sort of transforming things into different forms, heat is lost as sort of like the great balancer to sort of make sure that everything is equal on both sides of the equation. Now, in the second law of thermodynamics, which we talked about before, this is a situation, obviously, where everything proceeds essentially to a state of disorder. And that disorder or the entropy essentially is the lowest energy state. So I don't want to beat that one down because I thought we covered it pretty well in terms of the last chapter. So that's already there in the notes. So a good example of the change in entropy. So for instance, if you take a look then at ice melting in water, here's a pretty good example. So clearly, first of all, there is a sense of high order, right? So basically a high energy level in the ice itself. Let's go ahead and express this in terms of entropy. So remember the lattice structure of ice, the reason why ice floats in water, that sort of rigid structure basically means that it has a high order, man. It means it's less entropy. So that means it's a very orderly system. Entropy is the amount of disorder. So as a solid, it's a higher order situation. In the water, it's going to be a higher disorder situation. So you're going to have a greater entropy here. And so ultimately then what the ice wants to do is wants to proceed toward a state of disorder. So it's going to achieve then that state, which means it's going to turn into a liquid. And as it melts, then it's going to be giving off heat. And then ultimately that's going to be realized as a melting process where all the ice now has achieved maximum disorder. And so that's, notice that's exactly where the universe wants to go. The universe doesn't want to freeze, however it does, but it wants to ultimately melt, essentially. So it wants to go to its lowest energy state, especially with ice, right? Because maintaining that really rigid structure is energetically expensive. That's a high energy state for the universe to deal with. So what this does then, it gets us to an equation that a lot of times makes biology students break out in hives, but it doesn't have to. And it's an idea that we typically run into when we get into thermodynamics in chemistry classes. It's what's called free energy, right? And so just like we said that energy is basically the ability to do work, the capacity to do work. Free energy is the amount of available energy that's available to do work. Now you can generate all kinds of energy, and technically energy has the capacity to do work, but not all of it is available. for you to use, is because, for instance, you could have different forms of energy that are less usable or less accessible than others. A good example would be potential energy, for instance. Not necessarily all that helpful, however, maybe kinetic energy is. Things like that. So this is the amount of available energy that you can utilize to actually get some things done. And the way we express this is in this equation where we have a couple of other variables, some of which you've already been introduced to, right? And that is to say that the free energy that we have in any given system is going to be equal to its enthalpy, which is essentially the amount of energy that's kind of pent up in the chemical bonds of a molecule, right? So this is kind of like inherent, the heat of molecular motion. Or in this case, it's stored energy in your chemical bonds. That's your enthalpy, the amount of energy you have capacity. So this is your potential energy, basically. It's the potential energy number. And then, of course, T is absolute temperature. This is going to be your Kelvin scale, right? This is basically a situation where you would use the mighty Lord Kelvin. And then S is entropy. This is unavailable energy. So this is energy that you do not have access to. So it's an energetic term, entropy actually is. So then the amount of energy that you have is going to be equal to the total potential energy minus the unavailable, which is going to be a function of temperature. So the higher your temperature, the more unavailable energy you have. So that's kind of the way it goes. So when you take a look at this, then if you have increasing enthalpy, that is going to be a large positive number in the H variable, which is going to typically be accustomed or associated with a high free energy. So it gives you the ability to do a lot of work. Now, what happens if you have a high temperature? Well, if you have a high temperature, it makes this variable more negative, which basically drops your free energy. So you lose the amount of free energy you have available to do work if you increase your temperatures to extreme measures. And then, of course, also if you increase your entropy, that's also going to make the same term, TS term, very negative, and that's going to drive your G number down. And so if you notice, the increasing S is the amount of disorder. So the more disorder you have, the less free energy you have. So that's basically how these variables work. So what you want to do then is you want to basically create a system where you can have the maximum amount of free energy in order to do all this work. And we tend to express this in terms of relative scale. And we tend to look at it not as discrete G and H and TS, but as changes in G. That's what delta means. Delta basically is the change of free energy. And so in this case, your free energy is going to be very positive when your products have more energy than your reactants. So basically what that essentially means is that you're getting a gain in free energy from your product. So it's kind of like getting an energy yield. It's getting payback for what you put into it. Also, we already mentioned if your enthalpy is higher and your S is lower, that's also going to give you a positive delta G. And so in this particular case, this is, if it's positive, right, this is your positive delta G. The big thing that I want you to come away with is this is not spontaneous. That basically means it does not go forward. The reaction does not go forward without energy. You have to put energy into this in order to get it to move forward. And since you have to put energy into it, we refer to it as endergonic, or into putting energy into the system. So it's a type of reaction that we refer to as endergonic. This is a positive delta G. Now, in a situation where you have a negative free energy number, that's negative delta G, this is a situation where it's kind of flipped around. This is a situation where your products have less free energy than your reactants. So what that means is you've sort of lost value in this particular case in terms of free energy. If your enthalpy is lower, that basically means you have not very much stored potential energy. In those bonds. And typically your entropy is higher, you have a lot of disorder, then that's going to give you a negative delta G. This generally is what's referred to as spontaneous. That means it moves forward readily. But it's not instantaneous. So it's not like basically if you put these together, you're going to get, boom, an immediate chemical reaction. So it's a little bit different between spontaneity and instantaneousness. So typically what will happen is this will release heat. And so as a result, it's referred to as exergonic, or releases heat, exit, to go out of. And so that's basically an endergonic versus exergonic. This is kind of what they look like graphically. So here you can see in an endergonic reaction, your products are higher in energy than your reactants. You notice that that's basically flies in the face of the universe. The universe wants to go the opposite direction, wants to go from a high energy to a low energy, lowest energy state. So this basically means you have to put energy into it. We've already seen that kind of with our uphill battle with the active transport, where you got to put energy into that one if we want to get up to the products. So that's going to be a problem. So that means if we need to do this reaction, we have to have some source of energy in order to do that, which means we have to have a sound energy plan in order to be able to energize this reaction. And an exergonic reaction, instead of just basically going straight down to a lower energy product, then typically what's going to happen is, in reality, what we have is, and the reason why it's spontaneous, but it's not instantaneous. The reason why it's not instantaneous is because we have this little energetic hurdle, this little hump right here, that we refer to as active energy or activation energy. And this little energetic hump is essentially going to block the forward progress of this particular reaction. So once we get up to this this hump, then it'll naturally spontaneously go downhill. But once it does that, it'll release energy, but it has to get over that hump first. That's the reason why it's not instantaneous, but it is spontaneous. And so this is basically a negative delta G. Now, I'm not going to really hang on this whole, delta G equals delta T minus TS. I'm not gonna really beat you guys up about that one. That's just kind of explaining the two different reactions and the nature of the realities of the reactions that we have in terms of endergonic or exergonic, whether they're energy requiring or they're energy releasing. Those are two important broad brushstrokes that we need to understand in order to be able to better understand the types of reactions that we're going to be seeing when we take a look at metabolic reactions and things of that nature in the next couple of chapters. So the activation energy itself is essentially this barrier. We saw that this is basically this barrier. And so it causes these reactions to move along very slowly so that they're not moving forward willy-nilly. Now, the reason why this is good is because it allows your cells to essentially have control over whether or not these reactions go forward. And when they do go forward, your cells can basically make very intentional decisions about when and where and how that these reactions go forward. That is to say that the reactions aren't stuck in the on state. They are controlled and regulated so that you can have some control over whether or not these reactions are turned on or not. So there's two different ways then that when you take a look at this very slow reaction rate because of this activation energy, this hurdle that you have to get over. Now, when you take a look at your reaction rates, they tend to be fairly slow. So how can you how can you speed these things up? Well, basically the way that you speed these up is by lowering both of them, basically lowers the activation energy. That's the way you speed up a reaction. There's two ways really that you can do this. Number one is you can add heat to your reactants, because remember, your reactants are going to be a little lower than your activation energy. So if you can increase the amount of heat in those reactants, it's going to move them up further in their energy profile, and it's going to allow them to get close to that hump so they can maybe get over that activation energy and move forward. We can do that. We do that in chemistry oftentimes. You add heat in order to facilitate a chemical reaction, to speed up a chemical reaction rate. So we do that all the time. However, is turning up the heat a very functional way of doing things, say, for instance, in our body or in a cell? The answer to that is no, right? Because ultimately, you can't just turn the heat up on yourself. You can't just increase your core body temperature without having huge adverse effects. So you can't really increase the heat in order to make this reaction go forward. But the other thing you can do is actually lower the activation energy specifically more discreetly. So rather than raising the reactants up to make that energy hurdle smaller, what's going to happen is you can also lower the hump, if you will, so that the jump isn't quite as bad. So the reactants can basically jump over that energetic hurdle. And so ultimately then what's going to happen is once you reduce that activation energy, then those reactants will have enough energy in them to basically get over that hurdle, and then it's off to the races. You're going down the slides. Think of it sort of like this. That little girl that we saw climbing up the slide and then going down as our example of potential energy, turning into kinetic energy and releasing that kinetic energy. Well, when you take a look at activation energy, you can think of activation energy sort of like being the stairs. So in order to actually get over that slide, you have to climb up the stairs. You have to have enough energy to climb up those stairs first. That's the energetic piece of it. And so you have to be able to meet that level of energy before you can actually go down the slide. And it's a spontaneous trip at that point, but you have to get up there first. And that's kind of what activation energy sort of provides us, that barrier that keeps us from just basically sliding forward instantaneously. Now, there's another topic, and remember I said that chapter 6 is kind of a grab bag of topics that are energetically related that kind of helps underpin some of our discussions in the next couple of chapters. ATP is the next topic in line for that. And so ATP is a nucleotide. So this is a nucleotide. It's in the nucleic acid family. And it is basically an adenosine triphosphate. And so just like any other nucleotide, it's got its three pieces. It's got its ribose sugar. It's got its adenine in this case because it is an adenosine. And then instead of one phosphate in its phosphates group, it's got three phosphates. And so the reason why this is important is because remember, those phosphates are basically electron rich in phosphates. That means that you have a lot of energy density in those phosphates. Remember, electrons are essentially equal to energy. And if you don't believe that, then think of it this way, right? So basically what's powering the lights right now is a flow of electrons. It's called voltage, right? So that flow of electrons is essentially being transformed into light energy and of course heat as well from lamps and things like that. So that basically is a form of energy. So electrons exactly are energy. They are a type of energy, a type of kinetic energy. That's electrical current. We actually saw that on our list that we just saw a few slides ago. And so whenever you have molecules that are dense and rich in electrons, it also means that they're going to be dense and rich in electricity, in energy. And so that's the reason why, for instance, when you take a look at a phosphate, it is basically an energy storage tool where you can have a lot of electron density packed onto those phosphates, and that creates a lot of energy. However, the bonds themselves are unstable. Why? Because the electron repulsion of so much electron density makes the phosphates want to fly apart. So think about it this way in terms of like reality TV. Imagine you have three people who hate each other's guts. I mean, just like diabolically hate each other absolutely. And then basically what you do is with these people, there's a lot of energy, a lot of tension associated with them, right? They're in the room, their hair standing on the back of their neck, they got their fangs out, they're ready to claw each other's eyes out. There's all three of them ready to go after each other. And so what you do then to them is you basically stick them all in a broom closet. Well, how much tension are you going to have inside that broom closet? You're going to have a lot, right? I mean, these people hate each other. So the second that you open that broom closet, that first person is going to be blasting out of there with so much energy that essentially it's going to blow you over, right? They're going to basically knock you over. You're going to be on your can because they're just going to be bolting out of that broom closet. And so that's kind of what these phosphates are like. You put all three of these things together and they're just wanting to fly apart because of so much tension created by all this electron repulsion all smashed together in this tiny space. And so what happens then is it just basically rifles off. That first phosphate really wants to rifle off. And so when you take a look at the hydrolysis of ATP, basically you get that third phosphate wanting to bolt off. And when you do, it's going to create energy, lots of it too. And that energy can be used and harnessed to basically drive molecular and cellular processes. So they've got also a reverse process, so we have to recharge it. So you can think of ATP as sort of like a rechargeable battery. So you can expend or hydrolyze ATP to generate an enzyme, and then you have to recharge that battery to basically get your ATP back. You can, however, further hydrolyze ADP into what's called adenosine monophosphate and another phosphate. You get a little bit more energy, but not as much. And of course, that last phosphate is the lowest energy form. So that one's pretty happy, right? And so this can get a little bit more energy, but certainly not as much as ATP. So you typically tend to just do this one right here, your ATP hydrolysis piece of it. And this is kind of what ATP looks like. So you can see here, here's your ribose sugar. You notice that you don't have a deoxy form. It's got this hydroxyl group on carbon number 2. So that's what makes it a ribose. Your adenine is what makes it an adenosine. So these two guys right here together is what we refer to as adenosine. And then, of course, you have your 3 phosphates, not just 1, 2, but 3 phosphates all smashed in there together. And these guys are going to be very, very unhappy, and they want to basically just fly apart. So when you take a look at the ATP cycle, the hydrolysis cycle, essentially what's going to happen is this is where the energy comes from in order to drive these endergonic reactions. So basically, this provides the energy to drive endergonic reactions. And so when you couple the ATP hydrolysis with the endergonic reaction, then the overall net, because you're adding energy to it, is a negative or an exergonic spontaneous reaction, which then allows the reaction to go forward. That's basically the idea. However, this is not something that you want to, you don't want to pack and store and hang on to ATP. ATP is intended to be used, right? So it's think of it as sort of like a bus pass, right? So you got a bus pass. It's only good for a couple of hours or for a round trip. This is not something you want to hang on to. You got to use it or lose it. That's basically what you want to do. So you're not basically going to be dumping this into fat reserves or carbohydrate reserves or anything like that. This is a purely consumable type of energy. This is something that you want to use and you intend to use. You don't buy batteries unless you intend to use the energy that's associated with batteries, and that's exactly what ATP works. So ultimately, if you want long-term energy storage, you have to use carbohydrates and fats, right? So this is not in the same ballpark as that discussion in terms of utility. As a matter of fact, what happens is what you end up doing is initially all of your energy, your energetic molecules are stored in the form of carbohydrates and fats. And what happens is through metabolic reactions, you actually convert your carbohydrates and fats into ATP so that you can basically use that energy and then kind of recharge it. So actually the energy that comes from making an ATP comes from burning and breaking down and liberating the energy that you have in carbohydrates and fats. So the amount of ATP that you have in your cells, it is truly a use it or lose it, couple of seconds. So that means you're making energy all the time. So this is something that as your cells are doing work, they're not just making ATP and hanging on to it. The ATP that you made an hour ago no longer exists in your body. You've basically consumed it for the most part. It's all pretty much gone. And you've basically working on a new batch of ATP. So you're constantly making ATP, which is your energetic currency. So this is a critical molecule. This is your energetic currency. It's your consumable value product that gets you what you want, which is the energy that you need in order to do your biological job. So here's kind of the hydrolysis sort of a thing. So you can see that from ATP, remember it's a hydrolysis, so water's involved. So once you break up your ATP, then you're going to be liberating energy, right? So this is basically what you really want there. That's going to allow you to drive your chemical reactions. This is going to turn you into ADP and phosphate. And then basically what you want to do is you want to use exergonic cellular reactions, basically with lots of energy in them, to basically pack that energy into creating another ATP. So you can see how the two kind of oscillate back and forth into this great cycle. So the next basic idea and big idea that we're going to talk about is catalyst, right? So the idea of how do you increase this ability to kind of move these reactions forward, and how do you speed up reactions? Well, one of the things that you always use is what's called a catalyst. So ultimately, one of the things that that a catalyst does is it can't you know, you have the laws of physics involved here, right? So a catalyst can't bend the laws of physics. That is to say, they can't take an endergonic reaction and make it exergonic. You can't do that, because an endergonic reaction is kind of wired energetically, inherently, the way it's wired is an endergonic reaction. So in order to create sort of pseudo spontaneity, what it has to do is it basically has to work with the reaction and speed it up by working on its activation energy. So it can't work on, so what this basically means here is it can't add or subtract energy to a system. That's basically what it's talking about here. So that's a no-no, right? That's a violation of the laws of thermodynamics. So all it can do is basically sort of stack the deck, and that's basically where the activation energy piece comes into play. So it can't really mess with the energy of the situation, but it can kind of screw around with this activation energy and make the energetic circumstances a little bit more favorable for this reaction to go forward. And so we kind of already saw it a little bit, right? So we saw our activation energy moving from our reactants to our products, but the activation energy, if you recall, is too high a hurdle for the reactants to move over. And we don't want to heat our reactions up because that's basically going to be heating up our cells, and we can't really do that functionally. So what we need to do is figure out a way to lower our activation energy. And that's exactly what these catalysts do, is they lower the activation energy. The hurdle now, considerably smaller, is easier for reactants to basically jump over that little hill now, and it'll be able to move forward. And so that's what a catalyzed scenario does for us. Now, for us specifically, in chemistry, you talk a lot about lots of different types of catalysts, but in biology, we only have one type of catalyst. That's an enzyme. So enzymes are specifically, remember, this is a type of protein function. So these guys are specific types of what we refer to as biological catalysts. Now, we normally talk mostly about enzymes. However, RNA can also be catalytic as well. So they can also be catalytic. We found that out in the 80s, actually, by one of our local professors at UC Boulder, Tom Check, who won the Nobel Prize for that. And so in all cases, regardless, all these catalysts basically will do one thing. They will lower the activation energy. This is one common thing that they commonly do. That's what they do for a living. Catalysts lower the activation energy. And they do this basically by, stabilizing bonds and kind of breaking bonds and things like that in between them. There's different types of mechanisms, but there's a couple of things that have to be true for all enzymes. The first one that's true for all enzymes and all catalysts. So a catalyst has these two pieces of its definition, and it has to be true. The first of all is a catalyst has to be able to speed up the reaction. That's one thing it has to be able to do. The second thing it has to be able to do is it's not consumed by the reaction. And so those two things have to be true. A good example of an enzyme that we have is like carbonic anhydrase, right? So what carbonic anhydrase does, it takes water and CO2 gas and converts it into carbonic acid. That's what it does. It's part of our carbonate buffer system that we talked about in the acid-base section of our class. Now, what does this particular reaction look like with and without an enzyme? Well, let's take a look at it without the enzyme. If you have water and carbon dioxide together without carbonic anhydrase, what you're talking about on a per hour level is about 200 molecules of carbonic acid production. It's not very much. Now, if you add the enzyme, then all of a sudden you've gone from 200 to now 600,000 molecules of carbonic acid being made, not per hour, but per second. So you can see how massive, massive efficiency is being put in here. So you've gone from just a small trickle to now just opening up the floodgates of production. So you're talking about, making just a little bit to all of a sudden now super high output and just massive amounts of this molecule, in this case, carbonic acid, being made. And so the idea of an enzyme is incredibly, incredibly important, especially in biology. Now, all enzymes have some common features about them. First of all, one thing that all enzymes will have are these little three-dimensional pockets or little folds or grooves or clefts called active sites. And these active sites are essentially for binding our substrate. Now, the substrate is the molecule that the enzyme does its work on. So it has to bind to it. And then typically there's sort of a precise fit to it. So one enzyme, one substrate, that's typically what you kind of see here. So you have this enzyme substrate complex that's sort of given by induced fit. Now, what this basically means is that, think of it this way. When we talk about induced fit, so here's what we talk about, right? So here we usually talk about, and this is kind of a biochemistry sort of shorthand way to sort of map this out a little bit. Just follow me with it. So E is for the enzyme. S is for the substrate. So initially what you have is an enzyme floating around with its substrate floating around, and the two of them haven't met each other yet. Then what's going to happen is the two meet each other, and the substrate finds its active site on the enzyme, and it forms what's called the ES complex, right? This enzyme substrate complex. And then the idea is that to a certain degree, what's going to happen then is you release the enzyme and you get your product, right? So that's kind of what happens. And these are all reversible, typically. And the idea in terms of what we learned by induced fit is like this. Now, originally what we used to do is explain the fitting of, say, for instance, an active site with its substrate as sort of lock and key. We also used to do things like this. We'd draw an active site that has sort of like this little triangular wedge piece, and then your substrate would essentially come in with the exact same shape. And that's very much the way that illustration-wise, we oftentimes will draw it. However, in reality, so this is what's referred to as the lock and key model. And that's the way we used to think, right? These enzymes walked around, they had these sort of like little pockets in them, you know, and they just kind of like looked for their shape, right? Sort of like a lock is a three-dimensional construct, and it's looking for the right shaped key to unlock it. That's kind of what we used to think of. However, when reality, what we actually have is what's called induced fit. Now, induced fit basically means that there is no pre-established pocket in just the enzyme by itself. So basically, in an enzyme by itself, think of it sort of like a beanbag chair. How many of you guys have had or have sat in a beanbag chair? Show of thumbs. Right? Does the beanbag chair, when you're just looking at it, does it look like a chair to you? Does it look like it's something that's designed to fit you? No, it just looks like a blob, right? An amorphous blob. It doesn't become clear how it becomes a chair until you yourself sit in it. So you yourself basically will show up, and then by virtue of you sitting in the chair, you'll start to kind of form this little cleft-like structure, and you'll basically kind of mold the chair, and the chair oozes around you. So when you sit in a beanbag chair, that little indentation of your body as the beanbag chair wraps around you is essentially the exact same mechanism of induced fit. You're inducing the fit of your body on that beanbag chair, which is the reason why beanbag chairs are like for everybody, because it doesn't matter what your body shape is. You just we all basically experience a beanbag chair the same way. We just kind of melt into it, and the beanbag chair just sort of oozes around us. The beanbag chair originally doesn't have a shape. It doesn't have like, okay, this is Mark's chair because it's shaped like Mark, or this is somebody else's chair because it's shaped like them. Basically, the beanbag chair is amorphous, and I induce the shape on the beanbag chair. So the beanbag chair acquires its shape. That is to say, its pocket that it accepts me is being induced. The active site is being induced by me. That's what induced fit is. So this is a beanbag chair mechanism. And so it's important, right? Because what this means then is that the ES complex is kind of a partnership between both the enzyme and the substrate. The substrate basically kind of forms its little pocket and sort of accepts its little active site inside the substrate itself. And then once you actually have the ES complex, then you can do your chemistry, and then it'll release as the product. All right, so that's kind of basic enzymology. So here's kind of what it looks like. So here, essentially, you can see that you've got your active site here. And then notice it's not exactly the right shape here. So as the substrate comes in, it's going to induce a little bit of shape in there. And you can see now how the actual active site is much more specific and much more, you know, fit around that particular substrate. So this would be the E plus S, and this would be the ES. So this is a complex of both the enzyme and the substrate. And now in this particular place, then the enzyme can do its work. So let's go ahead and take a look at an enzyme. In this particular case, we're going to be taking a look at an enzyme of sucrase, right? Sucrase is, in this case, an enzyme that breaks down sucrose. So typically enzymes, many enzymes, not all of them, but they'll end in ASE. So if I see the suffix ASE, I know I'm dealing with an enzyme. In this case, this enzyme is telling me what it does. It breaks down sucrose. And so you can see my active sites here. So for sake of, discussion illustration, we kind of make the lock and key sort of a format. But essentially what's going to happen is this active site is designed to fit only sucrose, right, which is table sugar. And so when we get our sucrose coming in, what's going to happen is it's going to settle down into this active site pocket. As soon as it settles down in there, notice it's already starting to distort those bonds. Water's going to come in, right, because it's going to be a hydrolytic reaction. And what's going to happen is going to break that bond. As soon as it breaks that bond, it ceases to be sucrose and it becomes glucose and fructose, in which case now you're talking about products, not substrate. These pockets are only designed to fit substrates, not glucose and fructose. So it kicks those glucoses and fructose out. And then what you get then essentially is your sucrase back with the active sites. So when we take a look at sucrase then, and let's see whether or not this actually conforms to our two components of a catalyst, right? So first of all, does it speed up the reaction? How long does it take for sugar to break into glucose and fructose? If I took a pile of sugar and I put it on the table and I ask you to come back in 3 hours, is that sugar still going to be there?
Yes.
Right? If I have you come back in a year, is it still going to be there?
Should be.
Right? How many of you guys have had the bag of sugar in your pantry and it's been there for, how many years has it been in there? Is it still in there? Is it still sugar? So at this point, we're talking about years, right? So did it speed up the reaction? So I know what you guys are thinking. You're probably thinking, well, how fast was this? Well, let's take a look at this. This is basically milliseconds. So what do you think? Did the enzyme speed up the reaction? Yeah, right, by a lot. So your sucrose would basically be sitting there for years on its own. Sucrase is doing it in milliseconds. Let's take a look at the second one. Is it consumed or changed or altered? Well, no, because the sucrose you end up with here is the same as the sucrase that you have over here. So ultimately, this basically, once you actually finish, then this sucrase can go right back and grab another sucrose molecule, and you can just do it over and over and over and over and over again. So it's not consumed. So it fits the bill. It fits both definitions of a catalyst. So when you take a look then at an enzyme and a reaction that's driven by an enzyme, it's governed by how much enzyme you have, certainly, right? And it's also governed by how much substrate you have. And one intrinsic property of enzymes, which is what's called processivity, that is to say, how quickly can enzymes turn over a molecule of substrate in a given amount of time. Some enzymes are very, very fast, and some enzymes not as fast. So what can we do with these? First of all, with enzymes, they're very plastic. They're driving all sorts of chemical reactions. We have enzymes in organelles. We have enzymes in the cytoplasm. We have enzymes pretty much everywhere. We've even learned last chapter that we've got enzymes at the plasma membrane. So we've got them everywhere. So we have enzymes that work as solo actors, right? They're basically folding up in tertiary structure and then they're active on their own. We also have huge multi-enzyme complexes that work together as a giant machine or as a team together. And so what we refer to here is oftentimes we refer to as a biochemical pathway. So for instance, you can basically take product of one enzyme is the reactant for the next, right? So like, here's a good example. Let's say, for instance, we have a starting product A, which is converted to B, which is converted to C, which is converted to D, which is converted to E. And then the enzyme that converts A to B is little a, and the enzyme that converts B to C is little b, and then C to D is little c, and then D to E is little d. And so in this particular case, the product of little a, which is B, is the reactant of little b. So you can see how you can link enzymes together in terms of reactions so that you can create this huge pathway, ultimately, which will get you to an endpoint. We see this often, and we see this a lot in metabolism. So there are a lot of biochemical pathways. There are fewer standalone reactions and many, many more of these types of biological pathways that we see. What this does is it basically kind of links together the production of a molecule in sort of a coherent chain or in a coherent team, if you will. And you can control these reactions in real time in close proximity to each other. So it's a more efficient way of working. It's kind of like having a work team work on the same problem where all members of the team are working in the same area in the same place so that they can work more efficiently. Now, what about this idea of non-protein enzymes? In this case, this is catalytic RNA. We talked about that a little bit. So ribozymes are actually what catalytic RNA are. These have the ability to actually do some sort of a catalytic work. They can essentially do work on their own. And these are really, really huge. This discovery seems like it's like a backwater, but this is actually a really huge idea. When we talk about molecular evolution and things like that, we talk about things like, well, how did all this come together, right? How do you have catalytic proteins that need to be developed by DNA code, right? Which also needs protein, by the way. So in order to actually make a protein, you need protein to make a protein, and you need protein to be able to interpret your genetic code. So how do you manage to get all of this together when you're needing the genetic code and then you need a protein in order to do it? It's kind of like the ultimate chicken egg question, right? It's like, well, wait a minute, how do we make proteins? Well, we make proteins by using proteins, but then how do we get those proteins, right? How did those come to be? And so this was always kind of the big boondoggle of sort of the DNA-based molecular development or molecular evolution ideas. And so when this came around, where we had catalytic RNA, this was a huge discovery, because what that meant was that perhaps the understanding of whatever this this kind of like molecular evolution came together. We always think, oh, it's amino acids coming together randomly. It's like, well, how do you do that though? Because you have to have the DNA information to inform the protein. So how do you get that chain of information going? How do you get that flow of information when you have to start off with the information in the first place? Where does that come from? And so the idea was that it wasn't a primordial world where there was DNA coming together to form protein. Rather, the idea was that the world in those days, catalytically speaking, was RNA, and that the catalytic RNA had sufficient catalytic capacity to where it didn't need proteins to be able to do some of these catalytic behaviors, thereby circumventing the need to have a protein in order to make a protein, because you would already have catalytic RNA. So this was a big discovery for those particular reasons. And it's also really a huge idea, because we now realize that RNA does so much more than we ever thought it did. There's just about anything we can think of, RNA has some sort of a play in it. So it's a much bigger deal and a much more important molecule than we had originally thought. And that's getting into RNA. So that's neither here nor there. So ultimately, when you take a look at the catalysis of RNA, you have what's called intramolecular catalysis that, as I say, it basically catalyzes itself. So this is like an RNA molecule that's catalytic RNA can actually bend back on itself and cut itself. That would be like an example of intramolecular. There's also intermolecular catalysis, where an RNA molecule relies on maybe another RNA molecule in order to cut it or something of that nature. So you have interaction between two molecules versus interaction within a molecule. So there's different types of catalytic ribosomes that we see here. The other thing that we also noticed with enzymes, which are now just non-protein pieces of it, is what's referred to as cofactors. So we have two different things that kind of go along. So what we're talking about now is sort of like accessories here to the enzymes themselves. The first one is cofactors. So typically these are we refer to as minerals. Oftentimes these are metal ions, like for instance, iron or magnesium or things like that. And so oftentimes these metals will interact with different bonds and they'll soften those bonds up or they'll make them less stable so they break easier. So these are oftentimes interjected in there for very important reasons. It helps to potentiate or drive the catalysis of what these enzymes are doing. So typically metal ions are driving the catalytic behavior. They're actually driving the chemistry. Of the enzyme itself. And then coenzymes, typically we refer to as their vitamins. So these are organic molecules, non-protein, but they're organic molecules that typically will provide certain structures. So for instance, a good example of both a cofactor and a coenzyme is in hemoglobin, right? So we talked a little bit about hemoglobin in terms of its quaternary structure. Remember we had 4 proteins, 2 alpha globins, 2 beta globins. Well, each one of these globins is going to have a prosthetic group called a heme group. So this heme group is basically this big carbonaceous cage. And that's just my artist rendition. So this basically carbonaceous cage is basically the heme. And then in the middle of it, it's complex with an atom of iron, which is what binds the oxygen. So the heme group itself is actually a vitamin B12 derivative. And the iron, of course, is a mineral. So you can see then you have basically both coenzyme and the cofactor associated with this hemoglobin. So then when you're taking a look at enzyme activity and functionality, notice there's a common theme here that we see, because before we'd actually met this list before, right? We met this list back when we talked about proteins and how to denature them. However, now what we're talking about is these same parameters, only to less extreme measures. So remember before we talked about how to denature a protein by cooking an egg, that's extreme temperature, or making cheese with a pH of 2, that's extreme pH. But now what you can have is essentially an alteration of enzyme activity by doing less extreme measures. So if you increase the temperature even just a little bit, you don't have to kill an enzyme to make it three-dimensional. So ultimately what can happen is you can just make it non-functional. So at lower temperatures, at lower temperature extremes, not cold temperatures, but lower temperature extremes, we can knock an enzyme out of its optimum range. So a good example of that would be to like take us, for instance. Now, it's probably true that if I turn the heat up on you guys, the literal heat, up to where it's like, gosh, I don't know, 120, 150, I could kill you, right? Now, obviously, I don't have to kill you if all my goal is to basically make you non-productive. Because all I need to do is just make it a little uncomfortable, right? I have to just knock you out of your optimum. If I make it a little warm in here, then you're not going to die. You're going to be hot, sweaty, right? But are you going to be productive if I make it really, really hot on you right now? Is that going to be your maximum productivity? If I make it really hot on you guys right now, what are you guys mostly thinking about? Are you thinking about biology or are you thinking about trying to get cool? Yeah, trying to get cool, right? You're not really thinking about anything else, are you? So notice what I did. I didn't kill you, did I? I just made you uncomfortable. I knocked you out of your optimum range, and thereby, basically, I made you unproductive. Same thing is also true here. Don't have to kill a protein to make it unproductive. Just have to make it a little less optimal. Same thing with pH. You know, differences in pH basically can make your proteins inoptimal. And of course, another thing that we didn't talk about before is binding of regulatory molecules. So we can regulate activity of enzymes with regulatory molecules as well. Here's kind of what it looks like. So in the top graph, basically what we have is two enzymes from two different organisms. One is from us, that's humans, and the other one's from like a geyser, right? So these are hot springs prokaryotes, really, really hot. They're close to boiling temperature. That's what they live in. But notice where the optimum for their enzymes are. So for us, our optimum is right around almost 40 degrees, right? Anybody know what body temperature is? What's your body temperature? Yeah, 37 degrees, right? Notice where this optimum is. It's right there next to 37 degrees. So our enzymes are actually designed to be optimum right around our core body temperature, which makes a lot of sense. You want your enzymes to be optimal around your temperature. Notice also what happens. It's like if you get a little too hot, a little over 40, you drop off the cliff, right? This is the reason why fevers are not good. Because basically, you get a fever, your core body temperature goes up. It doesn't go up very far before you're in trouble, and you're starting to cause really, really huge damage to your proteins, and that's not a good thing. Now, if you cool yourself off, you start to getting hypothermic, you have a little bit more staying power, but still you're kind of falling off, and that's also not good. For the hot springs prokaryote, notice their optimum is much hotter, right? So basically, they're coming in around 70 degrees. I mean, we are basically dead by the time 70 degrees comes around. So this is kind of an important idea, right? Basically, this particular protein is only functional in the environment that you were designed to be in. Whether your core body temperature is 37 like ours, that's where your enzymes are going to be optimal, or whether or not you're designed to be in hot springs, prokaryote hot springs, where your enzymes are going to be regulated at a much higher rate. Notice also what happens. Let's imagine that we go hiking, we see one of these hot springs, and we drink the water. We swallow this prokaryote. Oh no, it's a pathogenic prokaryote. It's going to kill us. Is it going to kill us though? Take a look at this. Would this prokaryote do us any harm if it entered our body? Don't know. Here's the thing. Um, the answer is, according to this, no. Why? Because look, the proteins are basically at zero function long before they get down to our core body temperature. So this prokaryote would essentially be dead in our body and therefore unable to render us sick. Now let's take a look at pH. If you take a look at pH, we're taking a look at two human enzymes. One is pepsin, it's actually is in our stomach. The other one is trypsin, it's in our duodenum, in our small intestines. The pH of our stomach is right around 2, right? But take a look at where the optimum for pepsin is. It's right around 2, 2.5, right about the pH of your stomach where it's supposed to be active and functional. Notice how the alignment of pH and optimum function is exactly aligned with the actual setup of your stomach as well. Now then, once it goes from your stomach, it's going to move into your duodenum, which is considerably closer to neutral, not exactly neutral, but closer to neutral. And so you notice that you have a pH of a little north of 6, not quite 6.5 for trypsin. And that's about where your pH of your duodenum is. So it's a little south of neutral. but it is certainly considerably less acidic than, say, for instance, your pepsin. Now, notice the reason why you have this, right? Because the reason why you do this is because when your stomach passes on your food to your small intestines, then the first thing that happens is your acid gets neutralized because your intestines are not protected from your stomach acid the way your stomach is. And so by neutralizing all that, you bring your pH up. But also what happens here is it kills your pepsin. So your pepsin is no longer active. And what pepsin does is it basically cuts up proteins. It's a hydrolytic enzyme that cuts up proteins. And so it's cutting up proteins in your stomach. However, as soon as it moves into your small intestines and it gets neutralized by your intestines, then it's no longer functional. Why? Because it is knocked out of its pH optimum. Therefore, you have to replace it with another hydrolytic enzyme that cuts proteins, in this case, which is trypsin. And as it turns out, a whole host of other hydrolytic enzymes as well coming from the pancreas. And so that's the reason why we see this, so we can see how the shift in pH also affects the shift in function of the enzyme itself. So you can control these enzymes with either temperature or with pH. And then the last piece of it is with regulatory molecules. In this case, the two regulatory molecules will come in two flavors. One is called inhibitors, the other one's activators. So inhibitors basically will do what they say they do. They inhibit the function of the enzyme itself, and then activators do exactly what they say they do. They basically activate or stimulate the function of the enzyme itself. Typically, an inhibitor is something that will bind to the enzyme and it decreases its activity. And you have two different types of inhibitors. A competitive inhibitor is one that will actually compete with the substrate for its active site. And so in this particular case, you can imagine that you have an enzyme that essentially has an active site. And so here's your substrate. A competitive inhibitor would basically be something that looks very much like the substrate, only now instead what happens is it's completely different. And so it'll actually kill that enzyme or turn it off, right? So basically you can't actually turn on this enzyme if you've got a competitor in there. They're competing for the same site. That's why they're competitive inhibitors. And then, of course, you have the non-competitive inhibitor, which is essentially an inhibitor that does not bind to the active site. So this basically does not bind to active site, but it binds to some other site. We refer to this as what's called an allosteric site. So here's an example of a non-competitive inhibitor. So in this case, the inhibitor will actually bind to some sort of a little cleft over here. And then when it does that, it changes the shape of the enzyme, making the active site unavailable. So that's what we refer to as an allosteric site. And so it'll change the shape of the enzyme, making it unavailable. So here's kind of an example. Here's our competitive inhibition. So you can see here, your substrate basically will have this little bottom lobe that it uses to bind to the active site. And then there's this little cleft here that it will basically drop down into. Your inhibitor has the little bottom teardrop, so it'll bind to that pocket, but it makes basically the active site unavailable for the actual substrate itself. So that's a competitive inhibition. It's like musical chairs. There's one chair, two molecules. Somebody's going to win. Now, the way you can determine whether or not there's competitive inhibition is by changing the concentration of inhibitors. So the idea is that if you have 10 people playing musical chairs, and there's only one chair, right? So there's one person who is kind of considered the substrate. They belong to the chair, right? But the other 9 people are imposters. Then the more of those imposters you have, the less likely it is for that one person to be able to sit in their chair, right? So if you have a one-on-one, then half of the time that person is going to be able to sit in their chair. If you have 2-on-1, then a third of the time they're going to be able to sit in that chair. If you have 4-on-1, then they're only going to be able to sit in that chair a quarter of the time or 25% of the time, right? So if you have 9 other people competing with them for that chair, then their chances of them sitting in that chair are very remote. So the more inhibitors you have, the less substrate you have bound to your enzyme. Now, in terms of a non-competitive inhibitor, here's a situation where you have this allosteric site, this sort of off non-active site region, where your inhibitor will bind to it. And what it does, you can see it changes the shape. So now all of a sudden, the substrate is no longer able to sit in there. This is a very common strategy that you have in order to regulate enzymes. Matter of fact, this whole thing can be used as sort of like an on-off switch. to turn enzymes on or to turn them off, depending on whether or not that regulator is there, that inhibitor is there. We see that all the time. Now we take a look at these allosteric enzymes. Because of their activation inactivation state, they basically exist as either an active or inactive form, right? This is basically going to be the on state versus the off state. That's kind of what that allosteric regulator does for us. And so the inhibitor then will bind to this off-site region, and it shuts down the enzyme, whereas the activator will actually increase your enzyme activity. So you can have allosteric inhibitors and you can have allosteric activators, just like a normal inhibitor activator kind of at this situation. So we take a look then at metabolism. What we really are looking at then is basically a series, a whole collection actually of reactions, chemical reactions that are in our body that we're doing all the time. And there's two different broad brushstrokes of these metabolic reactions, right? So these are all the chemical reactions essentially that are inside your body when you take a look at your own metabolism, everything, the whole kit and caboodle. Typically, you can actually divide these totality of these chemical reactions into two major groups. One is what is called an anabolic type of reaction. So these basically are building. So these build up structure or molecules. So for instance, an anabolic type of reaction would be dehydration synthesis, right? You're taking and you're building polymers, you're building structure with it. So that would be an anabolic type of a thing. Catabolic then is the other flip side of it. This is basically tearing down structure or molecules. This is your demolition side. And so a good example of this would be hydrolysis, right? We studied that one when we talked about major macromolecules, right? So where you're basically breaking down molecules or you're digesting things. So this is what's called anabolism and catabolism. You're either building things up to build your body mass or you're tearing things down like during digestion. And so we already talked a little bit about biochemical pathways, right? Where essentially you have a series of enzymes that are working on substrates that basically occur in a sequence. And we oftentimes will see this, right? So here we see our enzymes, the enzymes 1, 2, and 3. So you can see the initial substrate for enzyme 1 comes in. This is your initial reactant, which will then be changed by the enzyme into your initial product. So it's the product of 1, but it's also the reactant of 2, the second reaction. And so this will then become the reactant for enzyme 2 or the substrate for enzyme 2. It'll spit out a product now. So this is your next product in line. And this will become the reactant for the next enzyme in line, which will basically turn this into another product, which would be your fourth product in this case. And so this will become the substrate for the next and last enzyme in line, which will then spit out the final product. So this is your fifth product in line. The rest of these are referred to here as intermediates. Oftentimes we don't see these because they, as soon as they are made, are almost immediately converted into their next step. So they're oftentimes very difficult to measure because there's really not a lot of them. Usually what we see is the initial reactant or the initial substrate and then the final product. And we don't see these intermediates in between because they are quickly consumed as soon as they are made. This also leads us to a type of regulation that we want to take a look at in terms of some of these pathways, which is called feedback inhibition. And so oftentimes what will happen is with these feedback inhibitors, what we have is a situation where the end product basically shuts down its own pathway. So this is an example of a situation where this will bind to an enzyme, it'll shut down its own production. This is a way to regulate the production of these molecules. So for instance, if you end up having plenty of this, you have too much, and you need to shut down this pathway, then what can happen is the product here can feed back and turn off this pathway so that you're not just overproducing everything. And so that's something that's called a negative feedback loop. It's when a product will feed back and shut down its own production. And so the way this looks is like this. So here's a pathway. We have You have your initial substrate, which will basically come in, bind to your first enzyme. You get your first product in line, which will then move into the next enzyme as its substrate. You'll produce your second product in line. This will move into the last one, which will produce your final product in line. So these are your two intermediates here. And then when you have enough of this, what can happen is the end product here can feed back in an allosteric sort of a way. It can bind to that first enzyme. That'll change, notice, the site, right? So you basically have a shape change here. And that'll basically disallow the binding of that initial substrate. So you effectively shut down the pathway at this point. And so that's a pretty common strategy, actually, that you see across all of these biochemical pathways. Okay. So there's 6. On to 7. I told you these were going to go fast. Any questions on 6? Probably lots of questions. But once I give you guys the take home, then the idea is you'll be able to kind of go back, take a look at these PowerPoints and kind of slow it all down, hit pause, rewind, all that sort of stuff. And then kind of, work your way through these PowerPoints as you kind of work your way through that take home exam. My guess is the way you guys are probably feeling right now is probably pretty numb. Is that fair? That's even when the energetics chapters go slow, the numbing effect is a common effect. You just kind of feel like, wow, what just hit me? And that's a pretty common thing. Even like when we try to unpack it and sort of slow it all down, it's one of those things that can't go slow enough, which is one of the reasons why I do these quickly and I put the exam as a PowerPoint, as a take home, so that you guys can sort of slow it down at that point, right? This part goes fast. What goes slow is the actual, unpacking it all and sort of putting it down into your take-home exam. Okay, ready for chapter 7? Okay, let's do it. So now that we kind of have some of the energy underpinnings associated with some of these chapters, now we're going to be taking a look at is how to harvest this energy, in particular, how to liberate some of that potential energy that we have in chemical bonds so that we can actually make ATP. So the story of chapter 7 is the story of cellular respiration, which is the story of making ATP, which we know is our rechargeable battery, right? That's what we essentially need in order to be able to do anything that we want to do in terms of biological functions and processes. So that's basically what we want to do. Now, when we take a look at the flow of energy through living systems, we have 2 major watershed types of organisms, right? So we essentially have what's called autotrophs. So these are the guys who are going to be basically making their own organic molecules. So these are these highly energetic molecules. And so these are plants, right? So they're basically making their own food. There's photosynthesis. And then there's those of us who basically can't make our own food. What we have to do is we actually have to consume our own food. Those are heterotrophs. So basically, we eat. So basically, we consume food. So we consume our organic molecules. So autotrophs will make them, and heterotrophs will consume them. Typically, we consume autotrophs. That's what we do. But ultimately, we all use the process of cellular respiration in order to get this energy out of these organic molecules, right? So remember, we had these energy-rich bonds in carbon and hydrogen, and so we have to liberate this energy, get this energy out of them, and we use cellular respiration to do that. So remember, one way to get energy out of these carbon-hydrogen bonds is to essentially light it on fire. So there's a bucket of potential energy in these carbon-hydrogen bonds. And so if we light it on fire, we can combust them, right? So we can, but that's not useful to us because we get a lot of heat, fire, and light, but it's not going to help us as an organism. What we want to do is we want to basically turn this and take this energy and we want to convert it into a usable form. What we want to do is we want to take the potential energy that's in carbon-hydrogen bonds and we want to convert it specifically into ATP. That's what we want to do because that's our rechargeable battery. And so when we take a look at these carbon-rich bonds and these carbon-hydrogen bonds, we see a lot of them, right? We see a lot of them in carbohydrates, so that's basically our preferred source. We will also go after fats, right? So that's our next preferred, but we'll also deaminate proteins. That's something that we also do as well. Not a good thing, but typically we want to go for the first and the second ones first. And essentially what we have in terms of cellular respiration is chemical reactions, which is the reason why we do chapter 6 first, that essentially takes these molecules and through a series of oxidation reduction reactions, which is the reason why we cover oxidation reduction reactions in chapter 6, is through a series of oxidation reactions, we essentially liberate and pull out this energy, or we harvest this energy, and then we utilize it into a useful form. So we've already seen then how ATP can be used. Do you guys remember the mechanism of the sodium-potassium pump? So we've already seen in that case, right, the utility of ATP. Remember, the sodium-potassium pump, when it's binding and sort of moving, that's an active transporter, right? When it's basically going through the shape changes, it's going to be in sync with the hydrolysis of ATP. So ATP is basically what allows the energy for that sodium-potassium pump to change its shape. And then once it changes its shape, then it releases that phosphate group and then it changes its shape again, right? And so remember, if you recall, with that sodium potassium pump, when you're doing that sort of oscillating shape change, you're basically taking sodium, you're binding it, and you're dumping it in the outside. You pick up potassium, and then you change your shape, and then you're dumping the potassium in the inside, and you're kind of just doing that back and forth, right? So you're basically binding ATP, and you change your shape, and you let go of the phosphate, and then you change your shape. So basically you have this native shape and you have this alternative shape, and that's kind of the story of how ATP is used to energize one particular very important molecular and cellular process. And so the idea is if you don't have any ATP, then you're not going to be able to set up a sodium potassium pump. If you can't have the sodium potassium pump active, then you're not going to be able to set up a sodium concentration gradient. And if you can't set up a sodium concentration gradient, then you're not going to be able to utilize sodium channels. And if you can't have sodium channels, then guess what? You can't do something basic like basically send a nervous impulse. As a matter of fact, all of the neurons that are firing in your heads right now are not going to happen if you don't have ATP. So that's the reason why we're all making ATP, and the process by which we make ATP is cellular respiration. And so if you recall then that in cellular respiration, we are using a series of chemical reactions where we lose electrons and then we gain electrons, right? The so-called oxidation reduction reactions. And remember to sort of keep track of who's losing what and who's gaining what. You remember the mantra that I used before, Leo the lion goes grr, right? So a loss of electrons, that's loss of electrons equals oxidation. Gain of electrons, grr, so that's of electrons equals reduction. So Leo the lion goes grr. And so ultimately then, when you have a dehydrogenation, you have basically a loss of electrons, typically accompanied by protons. But when you take a look at a hydrogen atom, and this is important, right? Because what we want to do is we want to take a look at this. Remember, a hydrogen atom is one proton, one electron. That's what a hydrogen atom is. So here's your proton, here's your one electron. So if you were to lose that electron and have a hydrogen ion, what you essentially have is basically a naked proton. So essentially the idea of a hydrogen ion is exactly the same as saying there's a proton. So you'll hear the term interchangeably, hydrogen ion gradient, proton gradient. They're the exact same thing because a proton, or excuse me, a hydrogen ion is only one proton, one electron, and the ion is basically a naked proton. That's pretty much what it is. So there's a couple of molecules that are going to be important in terms of driving these redox reactions. When you're driving these redox reactions, you have to basically have receptors or people, molecules, if you will, who will receive the electrons, and then some that will give them away. Now, there are a group of molecules in cellular respiration that we need to be introduced to. They are nucleotides. So they're nicotinamide adenosine dinucleotides, or NAD plus is one of them. And what this particular molecule is what's called an electron carrier. So NAD plus will accept 2 electrons, that's its reduced state, and a proton, typically that comes along with the electrons. And it'll become NADH. So this is a reversible reaction. So oftentimes what I'll do is I'll write it like this. So here's NAD plus. And basically, I oftentimes will refer to these guys as sort of electron taxis. And the reason why I refer to them as electron taxis is because if you take a look at a taxi, right? A taxi is designed to pick people up, yes? Okay, thumbs, right? So, but a taxi is not designed to hang on to those people. What a taxi does is it picks people up, takes them to their destination, drops them off, goes back, picks up more people, takes them to their destination, drops them off. Never once does the taxi pick up the people, hang on to them, hang on to them, hang on to them, hang on to them. You're mine now, right? It doesn't do that. It's designed to pick people up and drop them off. So these particular molecules, these electron taxis, do the same thing. For instance, NAD plus, if you were to add 2 electrons to it, will become, so this is its oxidized form, right? Will then gain electrons, become NADH, and it'll have 2 electrons, so this is basically the reduced form. However, just like any taxi, it's designed to let these people go. So it'll also go reverse order and it'll dump these electrons off to some place. And so these electron carriers or taxis are critical in terms of basically picking up electrons and taking them somewhere else and then delivering them. So that's what they do for a living. And so they're really important because what they do is they connect different molecules in different biochemical pathways as they're pertaining to electrons. So this is kind of what it looks like in terms of NADH, NAD plus. So let's say, for instance, here's an enzyme and here's an energy-rich molecule here, right? So you're going to get energy from it. And typically an enzyme will have an active site for NAD plus. So it'll basically kind of pocket right in there. So that's NAD plus, and your energy-rich molecule will basically bind to its part of the active site. Then you'll do some sort of chemistry. In this case, you'll dump 2 electrons on NADH, or NAD plus rather, and then it'll basically have that accompanying H on it. So it'll be leaving as NADH. That's basically what it does. And then this hydrogen will essentially will be gone from this energy-rich molecule, and you'll have this product basically that's been stripped, so it's lost electrons. So here's your gain of electrons down here, and you've lost electrons as your molecule. So remember what we said, electrons equal energy. So whenever you're doing this transfer of electrons through redox reactions, you are transferring energy. So in this case, what you've successfully done is you've taken an energy-rich molecule, you've transferred the electrons or transferred the energy associated with those electrons into an electron taxi, that is, in this case, NAD+. And then you can dump those off anywhere you want to do any particular task that you want. So when you take a look at the overall pathway of cellular respiration, there are a lot of reactions that are going on, a lot of them. And this is what we're going to cover is really the simplified version of cellular respiration. It truly is. But ultimately, there are a number of different types of electron acceptors. So there's a lot of swapping back and forth of electrons, a lot of giving and a lot of taking of electrons. And ultimately, then what happens is you're basically taking these high energy electrons out of these chemical bonds, and then you're transferring them to some sort of a final electron acceptor where you can actually get what you want. Remember, the goal here is to make ATP. Don't lose sight of the goal. It's easy to do, right? So what you're doing now is you're basically stitching together all these different chemical reactions, all these redox reactions, because you're trying to move yourself closer and closer and closer to the place where you can actually make ATP. And it's going to seem like it's going to take a little while to get there, but we're going to get there. So when we take a look at respiration itself, there's a couple of different types, right? So there's basically two different types, and it really comes down to whether or not you use oxygen. So oxygen is basically sort of defines the type of respiration. So when you take a look at aerobic respiration, so this is a situation where oxygen is necessary, so oxygen is required, because oxygen is what's referred to as the final electron acceptor. So that final batch of electrons goes to oxygen, and so that's its final electron acceptor. However, in some situations, it's anaerobic, so basically oxygen not required. Matter of fact, it's toxic, these guys. So you don't want to use oxygen here. It's like cyanide to them. In this case, it's some sort of an inorganic molecule, not oxygen, right? Because that'll kill you. So these are what's referred to as anaerobic organisms. So they're non-oxygen containing. Aerobic exercise, for instance, is associated with exercise that's facilitated and it's maximizes your breathing ability. So you want to be able to breathe. And then another type of anaerobic respiration, this is also oxygen not required, is fermentation. So in this particular case, instead of your electron acceptor being an inorganic molecule, it's an organic molecule. So that's a little bit different. So that is to say carbon containing. So notice the three different types of respiration are defined by who is the one who ends up with that last batch of electrons. Remember, think of the electrons as sort of like this sort of huge game of like this relay, right? You basically just hand off the electrons and they hand it off and they hand it off and they hand it off and they hand it off. And eventually somebody's going to get stuck with those electrons. So the question is, who is that final somebody and what are they? And so depending on who that final acceptor is of the electrons is what defines the different types of respiration. So we're going to be focusing mostly on aerobic respiration, at least in the first half, and then we're going to be following that up with anaerobic respiration at the end in fermentation. So in aerobic respiration, basically what we're going to be doing is we're going to be taking a molecule of glucose in particular. We're going to need oxygen, right, because it's our final electron acceptor, our terminal electron acceptor, and we're going to be producing CO2, carbon dioxide, and water, right? So notice that this is basically in our breath. So when you breathe out, you're breathing out CO2 vapor, and you're also breathing out water vapor, right? So we see that on a cold day. And so these are our byproducts. Now, typically, when we take a look at a free energy sort of a conversion sort of a thing, when we take a look at the amount of free energy that we get per glucose, we actually get like not quite, just a little south of about 1,000 kilocalories per mole of glucose. So in a cell, that's just in us, right? So in a cell, it can actually get higher than this. So that's really good. So what does that mean? That means there's lots of energy available. Remember, available energy, that's what free energy is, in glucose. And we want to get that out of there. And so since there's a lot of energy, you can't just liberate it all at once because it's going to be like, lighting a fire. It's going to be boom, this huge explosion. And we're going to get just a ton of energy all at once, and we can't really do that. So what we have to do is we have to sort of like squeeze it out a little bit at a time to make sure that we can handle that much energy. It's kind of the same thing we do with nuclear power, right? If we release nuclear power all at once, it's basically like an explosion, right? That's a bad thing. That'll kill us all. So what we do instead in a nuclear reactor is we sort of just, little bits at a time and small increments at a time, we basically sort of leach out the energy associated with these nuclear fuels a little bit at a time so that we can manage it. So that's essentially what we have to do with these chemical reactions, which is the reason why we have so many steps. So why we have long biochemical steps associated with this. So we already talked a little bit about the electron carriers. We actually have more than just NAD+. We have a couple of other types of electron carriers as well. We have another one that's referred to as FADH. And then we have another one a little later on in photosynthesis that we'll see. But we have a couple of these electron carriers that we use. And so these are very easily oxidized. So just like a taxi cab, they're not hanging on to people. They can easily pick them up and then give them up. So they can just pick them up and give them up. They have almost like no affinity, no desire to hang on to these electrons. They just grab them and pass them on. And so ultimately, that's the importance of these electron carriers. So when you take a look at these then, and in terms of this sort of the energetics associated with it, this is basically when we're taking a look at this, this whole stairway thing is what we refer to as an electron transport chain. Or an ETC. So if you take a look at it, you notice it's like rolling a ball downstairs. So here basically is your high energy electron with lots of energy in it. This is what we just got out. And this is what we have from food. So what we do then is as we pass it on, we're passing it on from a high to a low. And so it goes from the first step to a high to a lower energy, right? So this is a lower energy than the first one. And oftentimes what will happen is that the difference in energy will be expended and it can do work. So whatever work we want to do. As it goes down the next step, it's going down to a lower energy level. The difference here is going to be expended again, and we can use that to do work. As it keeps going down, it keeps releasing this energy, it keeps going down, keeps releasing this energy, and then eventually it's going to get down to its lowest level where it'll be picked up by oxygen. Typically also it'll be 2 hydrogens in there as well. So if you take these 2 electrons, now that are at their lowest energy state, plus 2 hydrogens and some oxygen, you pull them all together, then what you're going to get is water, which is where you get your water vapor from. In this case, the work, the energy that you're using here is going to be ultimately used in ATP synthesis. So this work actually goes to making ATP eventually. So this electron transport chain is critical because we don't only see this in cellular respiration, but we also see this in photosynthesis as well. So we see a type of electron transport chain as well in there as well. So when we take a look then at our ATP, we can see that our cells will use it. The amount of free energy that ATP molecule can give off is, instead of like 686, is only something more like 7-ish or so kilocalories per mole. So much more manageable. It's kind of the equivalent of, if you're versus this minus 686. So this is sort of like plugging your toaster into a nuclear reactor. So you don't want to do that. There's way too much energy. You're going to blow everything up. This is like plugging a toaster into your wall. So it's been stepped down, and it's been sort of at a level to where you can actually run appliances and not just fry all your circuits. Right? That's kind of what you're doing here. And so typically when you're making this ATP, when you're creating this ATP, you're taking this energy and you're bundling it into this ATP molecule. There's 2 major ways of making it. The first one is an enzymatic sort of a format, which is called substrate level phosphorylation. And we'll take a look at that. So this is basically where an enzyme will essentially transfer a phosphate to ADP. Specifically, it'll grab a phosphate, glue it onto ADP, and then it'll create that ATP. This is typically something that happens during the first series of steps that we see in cellular respiration called glycolysis. The second one, which is the big one, this is high output here. So it's a lot much higher output. This is the one we want. This is essentially where you use a separate enzyme called ATP synthase and essentially use the energy from a proton gradient to generate a lot of energy. So a lot of energy. So this is kind of like a hydroelectric dam. So similar physics. To a hydroelectric dam. Very similar to Hoover Dam. Right. So that's basically, there's 2 different levels of it. And so this is kind of like, this is our NADH molecule. So when you take a look at this NADH molecule, you can see your adenosine. This is the first structural component of it. You're not going to need to memorize this structure, but basically you can see this is your NAD plus. So you can see it's got a plus there. When you add your electrons to it, then one of that pluses is going to go away, right? Because you lose that hydrogen, and so that's associated with 2 electrons. Notice the positive charge on your nitrogen disappears, and that's basically where you get your NADH. So this is just for sake of completeness. It's not for sake of exam. I'm not going to grind you through, what is the structure of NAD plus and NADH. I'm not going to do that. That's just to sort of fill out the story. This here is the first mechanism of substrate level phosphorylation. Notice you have an enzyme here, which is called phosphorenolpyruvate. Excuse me, you have a molecule here, which is called phosphorenolpyruvate. So it's got a phosphate on it. Notice this little phosphate here. So what happens is very similar to the enzyme that we saw before for NAD+. It's going to bind to its own little active site in the enzyme itself, which is going to bind to your phosphate. And then the ADP is going to be sitting there in another pocket designed for it. And then what's going to happen is the enzyme is going to break this bond here, and it's going to smash that phosphate onto ADP, and it's going to be released as ATP. And then, of course, then you have, instead of phosphorenolpyruvate, you just have pyruvate itself, which is essentially phosphorenolpyruvate minus the phosphate. So basically what you're doing is, as an enzyme, you're grabbing onto ADP, you grab onto your phosphate donor molecule, in this case, phosphorenolpyruvate, and you basically take the phosphate, glue it onto the ADP, and then there you have it. There you have your ATP at that point. And so that's basically kind of like an enzyme level or substrate level phosphorylation. So what I want to start off with next, because it is our witching hour, is to go through the entire oxidation step of glucose as it goes through each of the stages. There's 4 stages: glycolysis, pyruvate oxidation, Krebs cycle, and then of course the electron transport chain with chemiosmosis, some of the elements of which we've already seen, because we just talked about that in the oxidative phosphorylation strategy associated with the high output ATP production. So that is where we are going to start next time. Any questions?